Welcome back, everybody. Welcome to the second video in a three-part series on the properties of matter and energy. We're going to pick up where we left off last time, which is on page 3 of the Chapter 3 lecture note outline packet. So make sure you have that handy and ready to go as we start the lesson. In the first video in this series, we learned how matter can be classified according to its form or its composition. In this video, we're going to be learning about how matter can also be described by its properties. What do I mean by properties? Well, what I mean is every substance has a set of characteristics that we call properties that allow us to recognize it and distinguish it from other substances. First, we'll talk about some specific types of properties. These are physical and chemical properties. What do I mean by physical versus chemical properties? Well, that's a good distinction to make. Physical properties are properties that can be measured without changing the identity and/or composition of the substance. So you can measure them and the stuff you had before you measured and after is the same. Some examples would be the color. We can look at something and describe its color without changing it. The shape is also another one of these physical properties. Mass, state, melting point, boiling point, density, these are all good examples of physical properties. Now, what about chemical properties? Chemical properties are properties that describe the way a substance may change or react to form other substances. When we measure chemical properties, we fundamentally alter the stuff we have, so they often involve changing the chemical composition. Some examples are burning something, whether or not it's flammable. We call this combustion. Other examples include whether or not a substance will corrode metals, or whether or not it's toxic and in what way it might be toxic. These are all examples of chemical properties. Now, there is also a category of properties that are very general, meaning they apply to all types of substances regardless of what we're looking at. These are known as intensive and extensive properties. An intensive property is a property that is intrinsic to the substance being looked at. Another way of saying this is that an intensive property is a property that does not depend on the amount of substance being examined. Regardless of how much there is, that property will stay constant. Some examples of intensive properties are temperature, melting point, boiling point, and density. So say, for example, you have two different pots of water on the stove. One of the pots of water has a gallon of water in it, and the other has a cup of water in it. Both are boiling. When you measure the temperature of either one, the temperature is the same. It's the boiling point of water. This is why boiling point is described as an intensive property. It doesn't matter how much stuff you have, that property stays the same. Now, another type of property that we run into are extensive properties. Extensive properties are not intrinsic to the substance being examined. Another way of looking at this is that extensive properties change depending on how much substance is being examined. Examples would be volume or mass. Say we had 1 cup of water. When we look at the volume of that water, we say that it's 1 cup. Now, if I increase the amount of water that's there, that property changes. We might have 2 cups of water or 3 cups. So the volume of the water changes depending on how much stuff we have. That's why we describe volume as an extensive property. Mass is the same way. Mass changes depending on how much stuff we have. Distance, that's another one. Length, height, width, that kind of thing. Those all depend on how much stuff we have, and therefore they're extensive properties. Now, sometimes these properties can help us identify whether or not we have a particular substance. Let's go into the next page and take a look at an example of that. Here's a question for you. Which type of properties, intensive properties or extensive properties, do you think would be most useful when we're trying to identify a substance? Well, that's right, we would want to use intensive properties. Any substance can have any particular extensive property because extensive properties change depending on how much stuff you have, not the type of stuff that you have. Intensive properties, on the other hand, are intrinsic to the type of material that you're dealing with, so they can be used as a way to help us identify compounds. One of the most useful of the intensive properties in helping us do this is density. Density is an intensive property that relates mass of a substance to its volume. Specifically, we can find the density for a given substance by taking its mass and its volume, and then dividing the mass by the volume. You might recognize this as a conversion factor, and that's because it is. It's a ratio of mass to volume, and we often use it as a way to convert from mass into volume or from volume into mass. So keep that in mind. Density is a conversion factor. Now, you probably already have a pretty good qualitative understanding of density. So when you pick something up and it's a lot lighter than you expected it to be, we would say it's not nearly as dense as you expected. But when you pick something up and it's quite a bit heavier than it looked like it should have been, we would say it's more dense. Let's take a look at a table I have below which shows densities of common substances. In this table, we see the first column shows different substances, and they're all liquids with the exception of table salt, which is a solid. We then have a column of the densities for those liquids in grams per milliliter. So notice the unit gram, which expresses a unit of mass, is divided by the unit of volume, milliliters. In the third column, we see various solid substances. This is followed by the last column, which is the density of those solids. Notice that we don't see a lot of densities here that are similar to one another. This is because density is an intensive property, and that's why also it can help us identify different types of substances. We can measure the density for a given substance and then compare it with known values to discover what it might be. Here's an example. Suppose you have a shiny gray solid with a mass of 10.895 grams. Its volume is 4.05 milliliters. What is the identity of this substance? Notice that mass and volume are not intensive properties. They're extensive properties, and we can't use the mass or the volume to help us identify what this stuff is. If we use the mass together with the volume, however, we can determine the density and therefore identify what stuff we have. So let's go ahead and find the density. Remember, density is a mass divided by the volume. So we have 10.895 grams, which is divided by 4.05 milliliters. This comes out to 2.69 grams per milliliter. Notice that I've combined the mass and the volume in the final unit. That's because density is a ratio, and the units will therefore be a ratio also. So now that we have the density, we can determine what substance this likely is. Notice we're dealing with a shiny gray solid. We should probably look over on the solid substances side for something that's similar. We have 2.69. Notice the only thing in that range is aluminum, which we would expect to be a grayish shiny solid. So it's likely this is aluminum. Now, sometimes we already know the identity of the substance we have, but we might want to use density to help us figure out some other property. Say, for example, we have a small sample of gold. Now, we don't know the mass of this gold, but we want to figure it out. We can place that mass of gold into a graduated cylinder. Graduated cylinders let us measure volume. Let's say that graduated cylinder already had 5.0 milliliters of water in it. After the gold was added, the new volume in that graduated cylinder was measured as 12.3 milliliters. Let's use this information to help us determine the mass of the gold sample. Now, just a note, it says lead sample here, probably a typo. I meant to have gold. How do we approach this problem? Well, first off, let's figure out what we're trying to do. We're trying to convert the volume of gold into the mass of gold. We're going to use density as the conversion factor that will allow us to do this. Density allows us to convert between mass and volume, or volume and mass. So our starting point here has to be the volume of gold. Notice that we measured the volume of gold by displacing an amount of water. That volume of water that was displaced, which is in units of milliliters, represents the volume of the gold nugget. Let's call this volume delta V. We can find delta V by subtracting the initial volume from the final volume. So it looks like delta V equals V final minus V initial. So let's put in our actual values. Our final volume was 12.3 milliliters. Our initial volume was 5.0 milliliters. So we should have 12.3 milliliters minus 5.0 milliliters, which gives us 7.3 milliliters. Do I have these significant figures here correct? Yes, because our volumes only go out to the tenths place, so does our answer from the subtraction. Now we still have to answer the question. We only have the volume of the gold here. We don't know what its mass was. So let's use the conversion factor density to transform this volume into the mass. So I'm going to multiply this volume by a conversion factor that has units of mass on the top, because that's where we're going, and the units of volume on the bottom in milliliters, because that's where we're coming from. So we have to fill in the density value for gold here. Notice that the density for gold is 19.3 grams for every milliliter. So we have to put the 19.3 next to the unit for grams and the 1 next to milliliters. How many significant figures should my result contain? That's correct. The result should only have 2 significant figures. That means we want to keep the first 2 digits in this result and then round the rest off. So what do we do here? Well, we have to look next to the 4. That's our least significant digit. We see next to the 4 there's a 0. So are we rounding up or are we rounding down? That's correct, we're rounding down. Rounding down gives us 140 grams per milliliter. Now, if you wrote down 141, that's because you're looking at rounding in the wrong digit. We need to look between the last significant digit and the one we're rounding. If you're looking out past the 0 at the 8, that's too far because we only have 2 significant digits. So, if you got this right, great job. We just figured out the mass of the gold by using its volume and density. Why might we need to do this? Couldn't we just have a balance and then measure the mass of the gold that way? Well, you could, but let's say you didn't have a balance handy. This would be a good way to determine it. You can also use this as a way to establish the purity of the gold, and that's actually still done today out in the field. Okay, so that's an introduction to density. Let's go to the next page, try a few more examples, and then talk a little bit more about physical and chemical changes. Now that you know how to use density as a conversion factor, this is a good chance to practice a few more problems. Go ahead and pause the video and see if you can come up with solutions to these 2 problems, number 3 and number 4. When you unpause the video, I'll show you my solution and walk you through it. In this first problem, we're given the mass of a penny, and we're trying to determine its volume in milliliters. Notice, however, that our density unit is not in terms of milliliters, it's in terms of cubic centimeters. That means we need an additional step. First, we need to convert the mass in grams to cubic centimeters. This is where we'll use the density as our conversion factor to do that, because it expresses grams in terms of cubic centimeters. After we have the volume in cubic centimeters, then our next step is to convert that volume into milliliters. For this, we need to know the ratio between a milliliter and a cubic centimeter. It turns out to be 1 milliliter is equal to 1 cubic centimeters. Once we have this, we can go through the dimensional analysis and determine our final volume, which is 0.35 milliliters. So if you got that one right, great job. Let's try number 4. In number 4, we're doing the same series of steps. We start with our 2.5 grams of osmium, and then we multiply it by the density conversion factor with 22.1 grams at the bottom and 1 cubic centimeter at the top. Next, we convert the cubic centimeters into milliliters using the 1-to-1 ratio between those 2 volume units. This gives us a calculated value of 0.113 milliliters. Now, of course, we need to round this down to 2 significant figures, so in the end, we get 0.11 milliliters. And if you got that one right, great job. Now, let's go back for a minute and talk a little bit more about the difference between physical and chemical changes. As you learned earlier, there is a difference between physical and chemical properties. Physical properties are properties that can be measured without changing the identity of the substance. This is related to the concept of physical change. In a physical change, matter changes its appearance, but not its composition. One of the important characteristics of physical changes is that they are often reversible, and they're reversible by other physical methods, meaning methods that don't change the composition. Here's an example: evaporation of water. When we evaporate a liquid water, we convert it from the liquid phase into the gas phase. Now, it's also possible for us to get that water back. We haven't changed it from water into something else. It's still fundamentally water. Let's take a look at some examples of physical changes and give them names. We've already discussed the conversion of liquid water into gaseous water. That's called evaporation or vaporization. Now, what's the reverse process, where we take a gas and we turn it back into a liquid? That's right, it's called condensation. So notice that these two processes are reversible. We take a liquid and we evaporate it, and then when it cools down, it will condense back into the liquid state. This is a characteristic feature of physical changes. They're reversible. Now, do we know any other names for some of these physical changes? So for example, what do we call it when we take a liquid and we transform it into a solid? That's right, it's called freezing. What about the reverse of freezing, when we go from a solid state back into a liquid state? Well, that's right, it's called melting. Now, sometimes people even know the names that we give to the transformation of things like a solid into a gas, or a gas back into a solid. These come up a little bit less in everyday life, so we don't always happen to know the names for these. The name that we give the transformation of a solid into a gas is called sublimation. The reverse process, where we go from a gas back into a solid, is called deposition. This word deposition is a great descriptor for this process, because imagine taking a gas and then passing it over a cold surface and seeing a solid grow on that surface from the gas. We would say this looks like depositing the solid, so deposition's a great word for it. Here's an example of some of these changes. In the bottom beaker, we have some iodine liquid. That iodine was heated so that it vaporizes and enters into the gas phase. Now up above, we have a flask that has some dry ice in it, making it very cold. The iodine goes from the gas phase directly into the solid phase, and this is called deposition. Now we still have iodine as crystals and in the liquid phase down below. It's all still the same compound, and we can reverse all of these changes. So for example, the iodine crystals can be collected, melted, and then sublimed again. That's why we describe these changes as physical rather than chemical. A chemical change, on the other hand, is when a substance is transformed into a chemically different substance. So the substance at the beginning and the end are different. Chemical changes essentially cannot be reversed with physical methods. Some examples of chemical changes you might be familiar with are combustion or acid-base reactions. So if we take some baking soda and we put it in with vinegar, we turn the baking soda into carbon dioxide, and we turn the vinegar into something called a sodium acetate. This is an example of a chemical change because the identity of the substances at the beginning is different than the identity of the substances at the end. At the beginning, we have vinegar and baking soda. At the end, we don't. Let's go to the next page and look at some examples of different processes and see if we can assign whether or not they're chemical or physical changes. So let's take a look at this table. On the left, I have examples of different processes, and on the right, I want you to fill in whether or not you think this is chemical or a physical change. So go ahead, pause the video, and read through each of these. When you unpause the video, we'll discuss. Okay, so what we're looking for here is whether or not we think we can get back the original substance. If we can, after the process is complete, that would be an example of a physical change. Otherwise, it's chemical. So what about a penny? It turns out if we take a penny and we put it into something called nitric acid, that penny will dissolve. You'll see little bubbles form, and the penny won't be there anymore. Do you think it's possible for us to get that penny back without doing a lot of chemistry in order to do so? Well, that's right. It's an irreversible process, so therefore it represents a chemical change. What about distilling alcohol from sugar and yeast? If you don't know, distilling alcohol involves taking the alcohol, warming it up, and then it turning from a liquid into a vapor. That vapor can be then condensed in a condenser to get back the original liquid. Notice there I said the original liquid. That means we have alcohol at the beginning and the end. Therefore, this is an example of a physical change. What about frying an egg? Do you think you can unfry an egg? Well, the answer to that question is no. It's very difficult to unfry an egg. Give it a shot sometime. This is an example then of a chemical change because it's irreversible. How about burning wood? Can we unburn the wood? No. This is an example of a chemical change. And finally, what about a bridge rusting? Can we unrust a bridge? Well, not easily. It turns out rusting is an example of a very slow version of combustion. The bridge, when it rusts, is actually burning just very slowly. And as you know from burning wood, it's very hard to reverse that. So this is an example of a chemical change. Now, one quick note. It is possible to reverse chemical changes, but you have to use chemical methods to do so. So if you have, say, rusting, that's the forward direction, the reverse of resting does exist. It's called reduction. That's the reverse of oxidation. Notice, however, that reduction is a chemical change. If we reverse a chemical change, we have to use a chemical change to do so, not a physical one. Now, don't worry if the words oxidation and reduction mean nothing to you at this point. That's expected. We'll explain more about that later on. So now we've come to the end of the second section and the second video in this 3-video lesson series. I'm going to end here so that you can take a break, and then when you come back, we're going to finish up with energy.